Hello, Math 20-1. You have watched the video that's really cool about fractals and how what we think is um, always smooth isn't always necessarily so. Um, and now we'll continue on with our notes on 1.4 geometric series. So when you think about a geometric series, one of the things you might think about a context is cyber ethics and gossip. And I know that schools have really been looking at cyberbullying and so on. And as a society, we've been fighting to stay on top of how to treat each other well when we've got things like Facebook and Twitter and things like that, and things can be said. And we've seen certainly a lot of athletes and movie stars that have said things that would like to take back. But if we look at this particular context, an old adage says character is what you do when no one's watching. Cyber students, cyber ethics, and netiquette refer to the responsibility of social behavior. These terms are what people do online when no one else is looking. And if we think about a fractal tree of cyber, if one person gossips or starts a rumor about something and tells two people, and then those two people tell two people, you can see the sequence that this is forming. Obviously, if the pattern continues and we all tell two people, this sequence seems to be forming a geometric sequence. And how could we determine the total number of branches or people that know? Because at each one of these junctures, they're different people. This person is different than these two and so on. Well, we would have to be able to take the sum. And so we could have several different strategies and ponder what you might do by trial and error. And I guess as we develop these formulas, what's important to remember is that somebody had to develop these formulas, and wise young mathematicians like yourself just said, well, I have a certain strategy to do it by either trial and error or longhand by adding things up. But to add up 200 stages would be a lot of work. And so there has to be a better way. So just like with the arithmetic sequence, we also had its corresponding series. So if we have a finite, which does stop, if we have a finite geometric series, its sequent is the expression of the sum. This is its sequence, and if we just consider adding the terms together, we now have its corresponding geometric series. The general formula for the sum of n terms of a series is given by this formula. And this one doesn't come about as easy as Gauss's formula did, but that is the formula that you will be using. And this formula works great. And if you consider, well, what values do you have to know? Well, clearly you have to know term 1. You have to know the common ratio. And you also have to know n in order to use that formula. Now, just like we had with the arithmetic, we have a different version. We also have this version, and to use this formula, ponder, well, what values do you have to know for this? These tools, as we've talked about in classes, you've done your formative work, you have to be able to know which one you're going to use when. And I know that can be a little bit tricky, but you have to know which one to look at and how, and that's part of doing your formative work. But it's also understanding that given what you know, what values will you be, what values do you have in the question? And so you're looking for the easiest path. Why is there a restriction on the value of R? Well, clearly our ratios, right? You can't have a common ratio of 1. Why? Ponder that for a second. What happens when you constantly multiply by 1? What kind of sequence do you get? Now that you've pondered, you've come back, and if you ponder it and you say, well, if I started with a term of, it doesn't matter what you start with, but if you multiply by a common ratio of 1, let's say, well, you're just going to get 5 and 5 and 5 and 5. So you're never going to change. You're just multiplying by 1. It turns out to be a constant sequence. If you had 5 rocks and they never turned into more rocks, you'd have 5 rocks forever. So it's just sort of common sense that you can't have R equals 1. In this next example, we are given the question to find the sum of this series. So the first thing you need to be aware of is that they didn't say what type of sum this is. Now we are learning about geometric series, but we do need to start thinking about, well, because at the end of this unit, we're not going to be told what kind of sequence or series it is. But when we compare succeeding terms, we can see that it appears that there is a common ratio of 3. Therefore, it is geometric. So I'm asked to find a sum. I'm obviously going to have to use one of these two formulas. Whether either of them are useful or whether I have to do more work depends on what I know and how many things I need to know for these formulas. So let's look and see what we know. What do we know? Well, we do know that term 1 is 5. We do know that R is 3. 15 divided by 5 and 45 divided by 15. We look down the road to 10,935 and we have no clue which term that is. We know it's the nth term. That doesn't really help us because we don't know how many steps the frog jumped in order for him to get there. But we do know that it is the last term we have to add up. It is the nth term. So now we ponder these formulas. Well, this one doesn't look good because as you can see where my pointer is, that n is a problem for this. But when we look at this formula, it appears we have everything we need. We know R, we know Tn, and we know term 1. Therefore, we can simply sub into that formula and solve for Sn. In this case, we can use BEDMAS. Some people call it PEDMAS for parentheses, exponents, multiplication, division, addition, subtraction, but we multiply first, and we end up with the sum of n terms being 16,400. So that's one of the ways that that formula can be used given the information. We continue on, and in the next example, we are asked to algebraically determine the sum of this sequence for the first 7 terms. So again, using the formulas we've developed, we have 2 of them. Again, we ponder what are we given and what do what formula would best serve us in solving our problem. So we know that term 1 is 27. We know the common ratio is 1/3, not 3, because like we've done before, we always look, it doesn't have a common ratio, but when we compare 9 divided by 27 or 3, divided by 9, those all equal 1/3. So the common ratio is equal to 1/3. We look down the road and they do seem to tell us that n is equal to 7, and we don't know what term n is. Now, are either of these formulas going to allow us to calculate? Well, sure enough, the first one serves our purpose very well. And again, we're careful. It's going to take a little bit of math. You need to be careful how you use your calculator and use parentheses in order for you to come up with this answer. And we do not want a decimal. Okay, use your calculator to give you an exact fraction. We don't want decimals. That's not the precision that we want. Okay. We do say it is approximately equal to 40.5. Okay, so there's a version of both formulas and how they can be used. All right, we carry on to the next example that says how many terms of the series will yield the sum of 342. And as you ponder questions like this, again, you look at what you have and you consider, it doesn't tell you what formula to use. It doesn't even tell you that this is geometric, you guys. Right? So you need to be careful. And first, the thing you do, get used to the process you're going to have to follow. You first have to look at this sequence. And it didn't say it was geometric. I know we're in that section. But when you ponder and you say, okay, yep, minus 4 divided by 2, 8 divided by 4. Clearly, this is geometric because we always have a common ratio of -2. Get in the habit of start realizing that at the end of this unit, you're going to have to decide when each of these concepts is used, okay? Don't blindly use it just because each section is telling you. All right, so we ponder now, based on what we're given, which formula would I use? Well, I'm given term 1. I know I just calculated my ratio of -2, n is equal to, I don't have any clue, but the sum is supposed to be 342. So take the time, you ponder before you just listen. Ponder and see which one of these would apply. Would this one apply? Would that one apply? Take the time to have a look. Well, as you pondered that, you would have seen that, well, if I plug things in, they're asking for how many terms based on what I was given. I knew the sum of n, I knew term 1, I knew r, I was looking for n. It wouldn't have served us at all to go to this one because we didn't know term n, and more importantly, we were really kind of screwed because we wanted to find out what n was, and this formula doesn't even have n in it in terms of solution. So now the trick is to solve this equation, and we can cross multiply these two together and this one times 1. So let me just show you. So if you put a 1 right here and you cross this and this is obviously minus 3. And minus 3 times 342 gives us that minus 1026. And then we can divide by 2. And we end up with minus 513, and we can add the 1, and we get minus 512. And now this becomes trial and error. We've talked about our calculator. How many minus 2's does it take to be 512? And we could use trial and error, and I showed you before how to use your graph and calculator if you wanted, but it takes 9 2's to get there. So therefore, 9 minus 2's, so therefore n equals 9. For this geometric series, 9 terms must be added to give you that sum. The bouncing ball, okay? One of the famous, we saw a bit of a bouncing ball in geometric sequences. Now, we're going to talk about it here. If a ball was dropped, that was too quick. Ponder which of those ones you should highlight. Which of the graphs would represent the height versus bounce number? All right, and so you saw a bit of an applet in the previous lesson on 1.3b on that. Which one of these? Well, if you've taken the time to think yourself before you just watch, before you just see, it's actually this one here. And the reason is, if you look, this ball has an elasticity of about a half. And if you look, each time it bounces, its maximum height comes only about half of the previous bounce. Every time it's about half. So that's the one it would look like. That is a geometric sequence that's referring to. Okay, so these ones here wouldn't make sense because, number one, these are linear. They're always going down by the same amount, so that would be arithmetic. On this ball, this must be some kind of anti-gravity ball because it's getting higher and higher as it bounces. So is this one, and this one is an arithmetic anti-gravity ball, and this one is this one is falling, but it's falling more. The bounce heights become 0. That doesn't, well, I guess it does become 0, but they're dropping off by an inconsistent amount the wrong way. The bounce heights shouldn't be dropping in that way. The ball is dropped from a height of 100 meters. It has an elasticity of 40%. So it's that same ball that we had before, where it only bounces up to less than half of what it was. The question is, calculate the total distance that this ball traveled by the ball when it contacts the floor for the 5th time. So when you're given a question like this, the best thing to do is to draw a picture of exactly what's going on in the situation. So if we ponder this, first thing we do is, okay, well, we'll take the ball and we're going to start way up there at 100 meters. And we dropped it. So it drops 100 meters. What does it do then? Well, then it bounces back up and it comes back down. Then it bounces up and back down. Then it bounces up and back down. And then it bounces up and back down and so on, okay? So that would be a map, and as you can see, it touched 2, 3, 4, 5. So now we have to decide what's the total vertical distance that the ball traveled, and we need to take the sum of the upward and downward distances. So we didn't throw the ball up in the air. By the sounds of it, it was dropped from a height. So we do not have this red distance. That distance did not exist. There is Sally, And she actually has the ball up here. There's her long hair, and she has the ball in her hand right there. So she's actually standing at 100 meters. But we do have to remember that there is an up distance of 100 meters as well. So when you ponder how you might calculate the total, we need to find the total sum of all the upward and downward distance of the first 5 terms. All right, so if this is the first term, is 100 is the first, and then 40 was the second, then 16, so 1, 2, 3, 4, 5, then we need to find the sum of the distances for the first 5 terms. And the reason we're taking twice the sum of 5 is because really there's an up and a down for every term, except the first one, because Sally was up there holding the ball. So we'll take twice the sum of the first 5 terms minus 100 for the fact there was no up. There was no up for the first bounce. Keep in mind though, a different context or a different question could have an up. So don't assume that all questions will always be subtracting. This isn't something you need to read the question. We could say that Mariah threw the ball up in the air 100 meters high and then it bounced back down, and then find the sum, and then you wouldn't be subtracting. So it's all about whether there was an up or not. So we pick which formula we use and we look back like we've been doing. Term 1 is 100, ratio is 0.4, the number of terms we had was 5, and the sum of the 5 terms is what we're looking for. We don't know what term n is, so we could use this formula, and in the blink of an eye, we have twice 164.96 minus 100, which gives us a big total of 229.92. The total distance traveled was 229.92. Now, there can be many questions. We're not possibly going to be able to ask every possible question that can be asked with these formulas. So this is just about giving you a little different context and asking for something different. So in this one it says determine the first term from a series. You're developing skills to use these formulas in weird and unusual ways. So in this case, somebody told you, hey, the common ratio of a geometric series is a quarter, and the sum of the first 4 terms is 1275. What is the value of the first term? And again, I would like you to try these questions without just going here, but without just going straight to the solution. But look at the formulas, and both of them have term 1 in it, right? So either formula you might be able to solve, but we need to be clear on what was told. So when they tell us that the common ratio is a quarter, they are clearly telling us that the common ratio is a quarter, right? They told us that term 1, well, that's what we're looking for. Do we know what n is? Well, they do talk about 4 terms, and we do know the sum of 4 terms is 1275. Do we know what the 12th term is? Sorry, do we know what the 4th term is? And we don't. We don't know what that is. That's a question mark. So now, can we find one of these formulas that will help us? Well, this one won't, because it's got term n in it and we don't know term 4. So this is our best bet. We sub in the things we know, and voila, we have got, or bazinga, as Sheldon would say, we've got a situation that allows us to solve. And now it comes down to algebra. And can we cross multiply these two things together so that we can do some good work? So you need to, again, a quarter minus 1, that's minus 3/4. We'll cross multiply, and we end up with this, which then we need to multiply by the reciprocal. And if you're wondering how they got to 960, they simply said, oh, I remember this. If I multiply this side by 256 over 255 negative, and this side by minus 256 over 255, because multiplying by the reciprocal blows everything up, and that becomes positive, we end up with a nice positive 960. The math shall set you free. And that, my friends, is the end of 1.4. Carry on and do your formative work.